Okay, calculus, let's finish up 15.3. So from the fundamental theorem of line integrals, it's clear that if f is continuous and conservative, then the value of f is the same for every piecewise smooth function or smooth curve from one fixed point in R to another fixed point. This result is described by saying that the line, the integral over c of f, the dot product of that and dr, is independent of its path in the region R. So not only, we're talking about this at the beginning, not only if we have a potential function do we just subtract, it doesn't even matter the path we take from those 2 points. It could be two radically different things. As long as the potential function is there, it doesn't matter. So if f is continuous on an open connected region, then the line integral is independent of path if and only if f is conservative. So let's remind ourselves what it means for f to be conservative. In 2 dimensions, that's if the two partial derivatives are equal to each other. And in 3 dimensions, that means all the subpartials need to be equal to each other. So for the force field given by f of x, y, z equals e to the x cosine yi minus e to the x sine yj plus 2k, show that it's independent of path and calculate the work done by an object moving from 0 pi over 2, 1 to 1 pi 3. So to show that it's independent, I need the yth partial of the I term and the xth partial of the j term to be equal, then zth partial, xth partial, and then zth partial and yth partial all the way down. So what is the yth partial of, we'll call this m, n, and k of m? When I take the partial with respect to y, it should just be negative e to the x sine y. The x partial of n is negative e to the x sine y, yeah, because it's e to the x. Now let's do the zth partial of m. So those are equal. That's 0. And the xth partial of k, 0. And lastly, we need to do the zth partial of n, 0, and the yth partial of k, 0. So they're all equal to their counterparts, which means this is conservative. So since it's conservative, we now need to integrate with respect to x, y, and z. The integral of e to the x cosine y with respect to x is e to the x cosine y plus some functions in terms of y and z. The integral of negative e to the x sine y with respect to y is e to the x cosine y plus some function of x and z. The integral of 2 with respect to z is 2z plus some functions in terms of x and y. So what do we actually need here? We need an e to the x cosine y, and we need a 2z, and then any function. So our potential function should be e to the x cosine y plus 2z plus a constant, because it is an integral after all. So we're plugging in the 2 points now. So let's plug in our endpoint, f of 1 pi 3. That becomes e times the cosine of pi plus 2 times 3 plus k. Cosine of pi is negative 1. So this just becomes 6 minus e plus k. What about f of 0, pi over 2, and 1? Becomes e to the 0th, cosine pi over 2. That's 1 times 0 plus 2 times 1, which is 2 plus k. It's just 2 plus k. When I subtract them, 6 minus e plus k minus 2 plus k, I get 4 minus e. So the work done between those points is 4 minus e, regardless of path, because it's conserved. Okay, one last thing in 15.3. A curve given by r of t for a is less than t is less than b is closed if r of a equals r of b. By the fundamental theorem of line integrals, you can conclude that if f is continuous and conservative on an open region R, the line integral over every closed curve C is 0. So let f of x equal mi plus nj plus pk have continuous first partial derivatives in an open connected region, and let C be a piecewise smooth curve in R. The conditions listed below are equivalent. F is conservative, that is, f is the gradient for some function. The dot product of f and dr is independent of path, and f and dot dr equals 0 for every closed curve C and R. So evaluate over C f dot dr, where f of xy equals y cubed plus 1i plus 3xy squared plus 1j, and C1 is the semicircle path from 0, 0 to 2, 0 as described in this picture. There are 3 ways to do it. We just saw the 3 equivalents. Okay, so let's see. We're going to let t go from 0 to 2, and x be t, and y be 0, because y is not changing over this regardless of path. Like, we can go from 0, 0 to 2, 0. C1 is a semicircle path, but we know by rule that the work traveled from around the semicircle should be the same as the work traveled here if the conditions are met. Are the conditions met? xy cubed, xy cubed. So we're good there on the multi-term thing, so it should work. What does that mean? It means my function is ti plus 0j, which means my derivative is just I. My function, in terms of plugging in, the y cubed and y squared are going to kill both terms because y is 0, so just become I plus j. Now when I do the dot product here of these two, I times, like 1 times 1 is I, so it's just 1, and then 0 times 1 is 0, so it's just the integral from 0 to 2 of 1 dt, which is t from 0 to 2, which is just 2. So I think that's the easiest way to do this problem, but there are 2 others that you can do, and that is all for 15.3.